Okay, so now let's do an example circuit that utilizes this concept of mutual inductance and also explains through a practice exercise the use of the dot convention. So we're going to have a current source that's delivering current to a load. That load consists of a 5 ohm inductor. We then have, sorry, a 5 ohm resistor, and we've also got a 16 Henry inductor. It's got a dot convention such that that is the dotted terminal. That's connected with a 20 ohm resistor and a 60 ohm resistor. And then finally we've got another branch of the circuit that only contains an inductor. That inductor is 4 Henrys and its dotted terminal is here. There's a mutual inductance between the 4 Henry inductor and the 16 Henry inductor of a value 8 Henrys. And what we want to do in this circuit is write the mesh current equations that we would use to solve the circuit. We're not actually going to solve the circuit, we're just going to write the equations for it. So to do that, what we need to do is establish the current values. I'm just going to call that the generated current. So we need to establish the current values in the different meshes. We've got this mesh here. The current is clearly IG. We've got a mesh current here. I'm going to call that I2. We've got a mesh current in the top. We'll call that I1. So what we need to do now is apply KBL and KCL to write the equations that govern these. So let's start at the top one, the mesh containing I1. So we've got if we analyze I1, it's going to enter voltage polarities such as shown there. So what we would say is I1 times J omega times 4 Henrys plus I1 minus I2. Since it's the mesh current method, there's a differential current flowing there, which is I1 minus I2. We multiply that by 20 ohms. We've got I1 minus IG times 5 ohms. So that takes care, not right in ohms, just times 5. That takes care of the mesh current for the top node, except for this mutual inductance. So the mutual inductance of 8 Henrys is induced in 4 Henrys by the current flowing through the 16 Henry device. We see that the reference current flowing through the 16 Henry device is IG minus I2 if we want. And if we take that as the reference current, we see that the reference current enters the positive terminal here. So I'm going to just draw the mutually induced voltage over here. It's going to be plus minus Vm. That's going to be the polarity. We see that it points in the same direction as the existing voltage across the 4 Henry, or the self-induced voltage across the 4 Henry inductor, and so therefore the last voltage in the mesh current equation for the top part of the circuit is going to be plus Ig minus I2 times J omega times 8. So that's for the top mesh. Now let's analyze the mesh containing the current I2. So I'm going to erase these polarity markings here because the polarities are going to change for this analysis because we're using a different reference current. So I'll erase all those. Fix my circuit. So I2 is going to be my reference current here, so plus, minus, plus, minus, plus, minus. So if I just write the mesh current equation for the 3 passive devices there, I would get I2 times, oops, not I2 times 20, it's I2 minus I1 times 20. That's the voltage drop associated with a 20 ohm resistor. The voltage drop associated with the 60 ohm resistor is just I2 times 60. Voltage drop associated with the 16 Henry inductor is going to be I2 times J omega times 16. So the last thing that we have to worry about now is the mutually induced the voltage due to the mutual inductance. Excuse me. So we come up here and we see that I1 in this case is the reference current. I1 enters the positive terminal. That means the induced voltage due to the mutual inductance is going to be plus minus Vm in that indication, which is opposite. So in this case, we need to subtract this. It's going to be minus I1 times j omega 8. Okay. So once again, I'm going to erase my polarity markings. Fix my circuit up a little bit. And I'm just left with this third mesh with Ig. So taking the two passive elements that are there, I've got Ig minus I1 times 5 ohms plus Ig minus I2 times j omega 16, and then I've got the mutual inductance associated with the 4 ohm device. Again, I've got the reference current causing that is I1. I1 enters the positive terminal here, therefore it induces a voltage that's positive at the dotted terminal down here, so the mutual inductance is going to be in that direction. So it's the same direction as the voltage drop across the element, so it's plus I1 times j omega 8. And so those are the oh, sorry, I forgot to write the complete equations for all of these. There we go. They all sum to 0, right? These are voltage. This is Kirchhoff's voltage law and Ohm's law, using the mesh current method for analyzing mutual inductance and illustrating the dotted terminals.